Alright, we're at the end of this long chapter, and we get to a point when we get to the end, you like to think about the beginning. At the beginning, we found the derivative by the definition, it was long and tedious. Then we learned the power rule, sum and difference rules, the product rule, the quotient rule, and then finally the chain rule. In addition to all those things, we found derivatives of trig functions. However, even though we did all that, there are some functions in which you just cannot differentiate. And some functions you can differentiate, but at certain values you won't be able to find the derivative. Those kinds of functions are called non-differentiable functions. There's a lot of syllables in that word. So figuring out where a function is not differentiable is what this lesson is all about. If any of these things are true, then f is not differentiable at a specific point C. I shouldn't say point, I should say value. 1, if f has a corner point at x equals the number c. I'll show you what that looks like in a moment. If f has a vertical tangent at x equals c, I don't think you've ever seen that before. And then the third case, if a function would be differentiable at a specific point, if the function is discontinuous at that point. Let's look at some examples. This first example, this function is differentiable every place except for this point here, x equals c. Pardon me, x equals 3. It's differentiable all these places and all these places. Now once again, f prime is the slope. If we just count spaces of this segment here, the slope goes up 1 and to the right 1. That's true all places here. So over here we would say the slope is 1. If we go over to this side and we just counted slope by counting spaces, we go up 1 and to the left 1. So at this point the slope is -1. When we get up here to the vertex, this vertex is shared by this ray, and it's also shared with this ray. So what would the slope of that be? One could argue the slope is 1. Someone else has an equal argument to say the slope is -1. Remember, for a limit to exist, I should say, for a limit to exist, it has to approach a single value. Since f prime is a limit, the derivative is a limit, this is approaching 2 values. From the left, it's approaching 1. From the right, it's approaching a -1. The slope is. Therefore, at this point, it's non-differentiable. Now you could see here, graphically, if I were to draw a tangent line through that point, I could draw a tangent line like this. I could draw a tangent line like this. I could draw tangent lines all different kinds of ways. If you can draw more than one tangent line at the same point, then that function is non-differentiable at that point. Graphically, when you look at this, this is called a corner point. There is a sharp edge right here at x equals 3. So the function is non-differentiable there. Here's another example of the function being non-differentiable at this point. Now keep in mind, any other point on this graph, this function is differentiable. Any point over here is differentiable. So if you were going to throw a random dart and hit this function, it is much more likely that the function would be differentiable at a point that it hit. The only place that it's not differentiable is this point right here. That's because the derivative is undefined. Similar reasons as the last one was. It's a corner point. We have a segment on this side. It hits this point and then it abruptly starts to turn into a curve. So at that point, in this case, we'd only know the x value is 3. This derivative of this function is non-differentiable. The third case that's mentioned above is that a function is not differentiable if it's discontinuous. So as we can see here from the left, this graph goes and it has this line once again. And as we approach from the right, we have this curve. So at x equals 3, it's not differentiable because the slope from this side is different from the slope from this side. It's jumping from one point to the next. If this ever happens at this spot, it's not differentiable. Any other place on the graph it is, but at x equals 3, in this case, it's not differentiable. This next one is the second rule, which says if there's a vertical tangent line to the curve at a point, then it's non-differentiable at that point. This is the hardest one to spot. Basically, this curve, which doesn't happen very often, but it does happen on occasion, essentially in this region, pardon me, the curve is concave left. Not really down, it's concave left. And in this region, the graph is concave to the right. When that happens, and it's happening in this graph, this inflection point, that's where it changes from being concave left to concave right in this case. At that point, the graph is undefined. Because the only way to make a tangent line to this curve at that point is to make a vertical tangent. And I know that what I just drew is not vertical. Let me try again. You know what they say, if at first you don't succeed, quit, because you're obviously terrible at it. That's a little bit better. This is the third case that I've shown you, where a function is not differentiable. And in this case, it's because the tangent line would be vertical. Once again, that happens when you have concave left, and then concave right, and then maybe later you'd have Kanye West. That is hilarious. Example A, find the x values at which the derivative is undefined. Please take a moment, pause this video, identify those x values on your own. And all you would do is you'd write down x equals, and then list all the places it's non-differentiable. When you're done, then unpause it and see if you got the same answers that I got. So here's all the places that I got. I got x equals 2, because at 2, let's go into the right 2, there's a corner point. It's non-differentiable at x equals 3, because the graph is discontinuous there. It's not differentiable at x equals 5, because if we were to draw a tangent line, it is going to be vertical. And I know that when you look at this, you can say, well, this is concave down. But if you zoom in on this, if you literally zoom in on this, you can see as we get closer, this looks more like it's concave left and then concave right. And then I also said that it's non-differentiable at 7, corner point, 8, corner point, and then 10, another corner point. So that's that. Alright, now we're to example B, and this is difficult, this example B. And it's trying to show you algebraically, by the definition of derivative, why this function is non-differentiable at a certain point. Specifically, why it's non-differentiable at x equals 0. So hopefully you can appreciate at this point, we can't just take this derivative with any special rule, because we don't have a rule for absolute value. If there is one that exists someplace out there in nature, I have never seen it. And quite frankly, if I did see it, I'd be scared, because an absolute value in nature is frightening. So let's find the definition let's find the derivative by the definition. Just to remind you what the definition is, f prime of x is equal to the limit, as h approaches 0, of the difference quotient, f of x plus h minus f of x divided by h. At this point, we can't substitute 0 in for h, because if we did, this will be undefined. We'd be dividing by 0. So to simplify this more, quite frankly, I don't know how to simplify it more because of the absolute values. So let's focus on, we want to show that it's non-differentiable when x is 0. So why don't we right now put a 0 in for these x's? Because that's the number that we're really concerned with. If we do that, we get the limit as h approaches 0 of the absolute value of 0 plus h minus the absolute value of 0 divided by h. Now that's helpful, because that means this is going to simplify to the limit as h approaches 0 of the absolute value of h divided by h. Now at this point, we can examine this from two different angles, and when we do that from two different angles, we're going to get two different answers. So let's do that. The two angles that I speak of, I'm going to break this off into two different parts. From one perspective, we're going to say that h is approaching 0 from the left. The other perspective, we're going to say that h is approaching 0 from the right. Because remember, for a limit to exist, a two-sided limit, the left and right limits have to agree. Because I'm at a kind of a standoff here with this equation, because the absolute value, I'm going to approach from the left and to the right, see what happens, and hopefully this absolute value is not going to be as big of a problem as it appears to be now. So if I have the limit as h approaches 0 from the left, essentially that means I'm putting a negative number in for h. Because if I'm approaching 0 from the left, it has to be a negative number. So I'm going to say that h is negative. Now when I do that, the absolute value of a negative number is positive. So this is going to change signs if I want to get the absolute value gone. Well, the bottom didn't have an absolute value, so it stays the way that it is. So this is going to simplify as the limit as h approaches 0 from the left, h divided by negative h is negative 1. To evaluate this limit, we simply replace all of our h's with 0. We don't have any h's. So this becomes a negative 1. So the slope approaching 0 from the left, approaching h from the left, is going to be negative 1. We'll show you graphically in a moment why that makes perfect sense. Let's check this out from the right. We have the limit as h approaches 0 from the right, means we're going to be putting in a positive number in for h, because to the right of 0 is positive. Going to exaggerate the positivity of h by putting a little plus sign beside it. The absolute value of a positive h is positive h. The denominator doesn't change, of course, because it was positive all along. There's no absolute value. A positive h divided by a positive h, anything divided by itself, is 1. To evaluate the limit, replace all the h's with 0. There are no h's, so this becomes 1. At this point, we can see why this limit doesn't exist. Why the function is non-differentiable at x equals 0. From the left, the limit equals negative 1. From the right, it equals positive 1. For a limit to exist, it has to approach a single number. Let me show you graphically why this makes perfect sense. The function that we were given is f of x equals the absolute value of x, which I'm confident that you know looks like this. It is made up of two different rays. The ray here on the right has a slope of 1, and it starts at the origin. Tell you what, let me redraw that. Let me make that black. That's not black. That's black. From the left, the absolute value function has a slope of negative 1. It looks like that, and I wanted to make that blue. So, remember, derivative means slope. The slope of this segment over here, this ray I should say, is 1. It goes up 1 to the right 1. The slope of this over here on the left is negative 1. And we know that by the graph, and we also know it because we just figured it out algebraically. The definition here, we approached h from the left of 0 at the point x equals 0. Because remember, we're trying to prove this is non-differentiable at the point here where x equals 0. Approaching from the left, we got negative 1. Look what the slope is, negative 1. Approaching from the right, we got slope is 1. And look what we got here, we got the slope is 1. At this point here, what's the slope? Is it negative 1? or is it 1? Because we have a choice, that means it's non-differentiable at that point. So that concludes the notes. Please do the homework, which probably will take you 4 minutes and 12 seconds. Then you can start working on the practice test, the review for this chapter, because our test is coming up rather quickly.